Hi guys, in today's video I'm going to talk about PWM, special kind of signal that is used very often in embedded software development. PWM stands for pulse width modulation, and it is sometimes used to do an action or encode information. And to use PWM in Arduino environment or photon particle, you use a function called analog write, which has following parameters. Pin, which can be any pin that has a prefix tilde, and value. It's a single byte, meaning that it's a number, integer number between 0 and 255, and frequency between 1 Hz to 65,535 Hz. And in this picture, in this slide, you can actually see what is a PWM. If you consider this as a signal through time, the lower section of this signal is obviously low and upper section is high. Let's say this example duty cycle 50%. So 50% of the time the signal is high, and 50% of time signal is low. High, low, and it is repeated through time, and thanks to pulse width. Pulse width is actually defined by the period, and the period is also defined by frequency. If you have a larger frequency, more frequent, it means that the period is shorter in time. If you have a frequency of 1 Hz, it means that the period is actually 1 second, one period in second. And what we'll do in this demo is we will dim the LED. Of course, for that we need the LED and a resistor, and let's begin. First, I'm gonna create the circuit. As always, I need a resistor, LED. Let's check the polarity. So this one goes to the ground, which is fine. And I need some ground exposed from here. And one more ground for the resistor, negative side of the LED, and I'll use the blue one to connect the LED to, let's say, D2. Okay, so this is the circuit. We had those before in our previous videos. And let's head back to the Visual Studio Code. And Visual Studio Code, there you are. I'm not gonna type the code, I have already example loaded here. I will just show you. Let's talk about the code. First, this is const integer pin LED. Actually, I need to rename this because this is one of the old naming conventions. I will right click on it and I will choose rename symbol to pin LED. I prefer using prefix pin, so I know that I'm talking about hold on please, because I'm talking about the pins in this case, so it has a prefix pin LED. Yeah, it worked, and I need to make this constant because it's not going to change. I have a value, which is the value of that duty cycle. It's 0, and it can go up to 255. And I chose a frequency of 100 because it's large enough, so I cannot see it. When I say I mean I as a human cannot see the frequency above 100 Hertz. I think if you know the frequency of the motion, where we register motion is 24 That's why all those movies and so on have 24 or more refresh rate. Change of pictures, frequency of changing is more than 24 pictures per second. That's a movie. Okay, in the setup I have a pin mode, obviously output for the pin, and then in the loop I'm calling analog write. Check it out. I'm calling analog write with the pin value and the frequency. All those are variables that are going to be determined here. First, I'm incrementing value by 1. So if you remember, it was 0. In the first loop, it's going to be 1 and all the way up to 255. And I'm checking if it's 255, I will set it back to 0. But I'm pretty sure I don't need this. Let's try it. And I have a return here because this is another example. So just ignore this part. So this is the end of loop. End of loop. So I'm incrementing value every 20 milliseconds. I'll flash the code. Let's just plug in the board, Cloud Flash. And what you could see now, but I'm pretty sure it will not be visible because of the camera, but that's a different kind of story. And the board is flashed. And you can see the light goes brighter and resets. Because this white resets back to, let me see if you can see it in the camera. Yeah, it's just, yeah, you can see the increase of brightness, which is cool. It resets because the overflow happens. Once a number in a memory, for example, I have 1 byte of for the value. Once it reaches the maximum value, it will overflow back to beginning, so it starts again from 0. And that's why you have this kind of like animation from low to high. And when I said that PWM is used for doing some action in this case is dimming the LED. And this is how LED dimmers work in all those light bulbs for the LED lighting. In previous lighting technologies, those incandescent lights, you had the option to lower the voltage and you get lower the brightness. In case of LED, you cannot do that. You can't lower the voltage to get something less bright and more bright. All you have to do is turn on and off more frequently. Let me show you how this looks on the oscilloscope. I have here the one I usually use. Let me just connect this to the digital output for the LED, and I'm gonna show it to you. So I'm using it in series. Parallel, sorry, and check it out here. So ignore the noise. What's happening here is that you can see, let me just scale it a bit down so you have more. Yeah, that's cool. So you have a signal here. It goes, when we said that the value goes from 0 to 255, it's actually defining the PWM signal, its shape. So the shape of signal is changing. You can see it becomes, here is more low and it gets more high in this case. And what's pretty amazing in this scenario is that LED is on and off. It's turned on and turned off, and it is happening 100 times per second. And our human eye is so, first it's amazing, but it's so imperfect because we cannot perceive the blinking of LED, but what we perceive is dimmer light. And that's so cool use of PWM. I'm gonna change the frequency, something that we can see. Let's say frequency 2 Hz, 5 Hz, for example. I'm gonna Cloud Flash. Wait for it to it's flashing. I think I'm gonna show you how the light looks. Let me see if this will, yeah, you can see the light being flashing, and it's flashing. I don't know if you can see the difference. Obviously it is flashing, you can see that, but it is flashing for a longer time. And if you take a look here, let me just set my oscilloscope, give it some time. Yeah, it's a bit confused now there. I'm gonna scale it down so you can see the signal, and voila. Let me just scale this as well. So it changes much slower. The change is slower because it's only 5 times per second. And you can actually see it also goes from 0 to 255, but it's blinking because it's not, the change is not fast enough. And this is how PWM works on LED. Remember it just lowers the brightness. And this is how LED dimmers work in your home. Next, what I'm going to show you here, I'm going to change the frequency. I mean, we already changed the frequency. I will just remove this part of the code, and now this part is active. What is this part doing is I'm changing the frequency. Frequency here is 5. I'm going to set it back to 0. Sorry, to 1, because it has to be, the frequency can't be 0. And in the loop, you can actually see that the value is constant now. It's 128. It is actually half a byte. It's 50%. It means that the 50% of the period, the signal will be high. Other 50%, the signal will be low. And I'm changing the frequency each second. So each second, the frequency will get higher and higher, until it reaches 65,000. I mean, you can actually calculate it's 65,000 seconds. We will not wait that long. You will not see any difference. So let's cloud flash. Again, I have my oscilloscope and my LED. Now it's being flashed. Check it out here. I'll try to keep it steady. So flashes are increasing. Each second the frequency is higher until second 24, maybe 20, you will no longer see the flickering. And I can see that in the camera you can actually see the flickering, but at some point, which is now, you no longer see any flickering because the frequency is just too high for our eyes to distinguish two states, on or off. I will just reset. So at the beginning frequency is 1, so you get half a blink, 1, and now we get to second frequency and so on. Let's check it out how this looks on the oscilloscope here. I mean, there's no need to reset from beginning, but the point is you can actually see those ups, highs and lows are getting more, sorry, let me get back. So they are getting narrow. So I need to zoom in into a signal to get it more detailed. So you can see that the frequency, with the increase of the frequency, the period is shrinking. It means that the period lasts shorter time, because in the x-axis this is time, right? So the width of this tiny square is, in this case, 20 milliseconds, and it's getting shorter and shorter with each second where the frequency changes. And that's it. This is how you change the frequency. I think you may notice that maybe in some, I had very cheap LEDs before, I mean home lights LEDs. When they have a dimming, once you lower the light being dimmed, you can actually see the flickering. It means that the manufacturer set the frequency a bit low. Maybe increasing the frequency will eliminate the flickering, and that might help. But nevertheless, I think more expensive, more good quality LED lights are flicker free in this case. To move on with the topic of PWM, let's talk about servo. So the servo, it's electric motor with 0 to 180 operating range. My servo is extremely cheap, and I don't think it's more than 45 degrees. We'll see this in demo. And it is PWM controlled. So the manufacturer of this servo has defined pretty much all the necessary information for you to control the servo, like frequency, what is the width of a signal to the leftmost, and what is the width to the rightmost maximum position. And of course you can use the library in this case. However, we will do this manually. We will control the PWM signal. However, to get exact values, we need to do some math. It's a simple math, don't worry. So in this case, what is said? First, let me just draw what PWM looks. I mean, I showed you in a slide. So this is like a voltage, and this is time. So this is one section of signal, let's say this, and what we can say that this is a period. So this is one period of a signal. Okay, and in specification it says that the frequency is 50 Hertz. So the leftmost, I will use the L, is 1 millisecond, and the right one is 2 milliseconds. So the question is, if you remember this analog write, it has pin value and frequency. The frequency is already 50. What we need to do is get the value for the L and get the value for right. It's unknown. It's very simple. First thing what we need to do, we need to get this P. What is the period? So the P is 1 over 50. And this is 1 over 50. It's 50 is the frequency. It's 1 over seconds. When you flip those, you will get, so the width of the period is 20 milliseconds. Let me just check, but I'm pretty sure it's okay. It's 20 milliseconds, so my math is okay. So we have a P, and the question is, the value is actually relative. So the question is, so this is the L, and this is right. If you imagine signal being from here to here, so this is L, and this part is right. The question is, what is the percentage? For example, if in our case the value would be 10, it's half of the period, so the value would be half a byte, it's 128. But in our case, so the value of L equals period, it's 20 milliseconds, times, so the value is period over, let me just check, times 255. It's the L over period, and equals to 1 over 20 times 255, and that's the value of 1/20 times 255. It is 12.75, because the manufacturer said that the leftmost position, so the lowest position, is at 1 millisecond, and the value of byte is 12.75. However, the byte is integer, it can't be a fraction of that, so we need to round it up. And we need to round it up into higher value, because it can't be lower than 12.75. So we round it up to 13. So the answer is 13. And for the other value, so value for the right is the right value in time units, so in seconds. It's 2/2 milliseconds over 20 milliseconds, which is actually we calculated the period from here. So times 255, that's a whole byte, and this equals to 20. Let's do the math. I don't wanna. It's 2/20, 0.1 times 25.5, obviously, right? It's 25.5. So that's the maximum value for rightmost position. It can't get any bigger than this, so we need to round it up to lower value. That's 25, and this is our answer. The value goes from 13 to 25. Now we can do all the sorry about the mess in the paper, my pen is not perfect, but and I lost the cap. So let's do the code. And the code, again, I will not write the code. Let me just check if I have it here. Yeah, I have it here. So first thing first, we need to connect the circuit. I will use the probes again so we can see the values. Just put them away. Disconnect the board while you're working. I will disconnect from PC. And now connect the servo. Connecting the servo should be a bit easy, because it's color coded. See here, the black color is black for the ground. I need some red here for the power source, so it's on 3.3, and the white one is the data. I'm using this kind of wires because I don't have any convenient connector here, so I'm gonna connect this to the ground. I can do it directly here. So this one goes to the ground, the red one goes to the 3.3. Be careful not to put it in USB, just 3.3. And the white one, we will put this one on D3 here, and this is servo. I put some cap on it so you can see the motion, hopefully, if this will work. And checking the code. First things first, const integer, as I had before. The name would be pin servo. So it will be pin servo. Wait for rename, and I put it on a D3 because D3 is also PWM. And the first value is 13, and frequency is 50. And I will just rename this into English. So this is increment. What I'm trying to do, I'm going to sweep from right to left and go back and do the motion of sweeping. And that's why I have this increment, which is, you will see in the code, it's a neat way to change the direction of increasing values. So increment is 1. And in the setup, I have a pin mode. Of course, the servo is output. And here I'm writing initially in the setup, I'm writing a value to the servo, to the PWM, the leftmost position, so 13, and I have a delay of 1 second here because I want to give servo some time to get back to the first position, because I don't know what is the last position of the servo. Of course, if you push too much, the servo will not have enough time to react, so you need to give it some time so it can move freely to the desired location. Here I'm having a delay, I think in 1 second it's more than enough. And in the loop I'm having analog write with pin servo value and frequency, the same thing I did with the LED. However, the calculation of the values is a bit different. First things first, I'm incrementing value. In LED example I had value plus plus, but here I have a value plus, in this case increment is 1. Okay, increment is 1, remember this. And I'm checking if the value is more than 25, which is not, and I'm checking if the value is less than 13. In this case it's not, because it's only, the value is now 13, incremented by 1, so the value is 14. What's going to happen, the value 14 is going to be written in PWM signal, and I have some delay here at the end of the loop, so to give time to the servo so it can move just a bit, let's say 1 degree in desired direction. And here, after the several loops, more precisely 24 of these, so the increment is also still 1, and the value is, so we are now at the value, for example 25, incremented by 1, it's 26, so it's more than allowed. So I'm checking if the value is more than 25, it means yes. What I'm going to do, I will decrease the value by, I will change the increments to negative values. So the next time this increment happens, it will start decreasing. So in the next loop, now the value of increment is -1, it will start decreasing. So value is equal value plus, now it's -1, and this is how you have the motion. And once the value reaches 13 here, it will start incremented again. So you hit the bottom of 13, go back. So check it out how this looks on, so I'm flashing the code, how this looks on a servo. I failed to flash because I failed to connect the board to the PC, I mean to the power source. So let's flash again. Interesting. Just a second. Okay. I made a mistake. See, it's the same thing that I warned you not to do. I put my pin, so I connected basically ground and reset. It means that the board is always resetting. I missed the hole, it should be 3.3. Now I can start the board. Yeah, it's okay. And I can initiate call out flash. Don't do that, okay? I do these things so you don't have to do. Now you know what happens when you connect reset. So the board is flashing, and you can actually give it some time. Here you can see the servo motion. Because this servo is very, very cheap, you can actually see it's, I don't know how many, 30 degrees, not more. So it should be 180 degrees, but this one is very, very cheap and a bit old, I must say. So it's not moving that much. And also it's not strong enough. It has, I don't know what the maximum force it can exert on something, but it's pretty strong enough to push a button on a keyboard or on a lightning or whatever, so you can attach it. I have seen some projects of people doing like this. So they connect a pen, so with some levers and wires and so on, you can push the pen button, turn on and off the pen using the servo like this. And that's it. I'm gonna show you how this looks on the oscilloscope. I have mine here. A moment. Just imagine if we were in a classroom and there were 13, 15 of these. You can actually hear the motion. So 15 servos with the students. It sounds like you're on a vacation on a coast with the crickets. That brings memory before COVID. So I connect this one to the ground. Yeah, I have a problem now. I need to expose this to the, I'll give it some time. So never do this on live, but I'm doing because I don't want to waste time. Okay, so now I have connected the probes, and let me just bring my good old, it's a pretty old oscilloscope here. So just bring the servo so you can actually see the servo motion here in one part of the screen. Okay, and I'm gonna zoom in. So sorry, zoom in here. Let's check this part here. So you can see the width, the time of single box in this, not single square, sorry, is 5 milliseconds. So this is 5. Let me just align those. So this is 5, 10, 15, 20. So this is 20 milliseconds, exactly what we calculated. And it goes, I will now zoom in into this part of the segment. So the width of single square here is 1 millisecond. And you can actually see it goes from 1 millisecond up to 2. Okay, from 1 to 2. And this is the motion, this is how servo is controlled. You can actually see being like this. Okay, so this is also an example how PWM is used to do some action. And of course you can encode information in PWM to different weights, could be a different symbol and so on, so you can send data over the signals. There are some cases where it is done, but there are much more efficient ways to send information. Nevertheless, you can also, that's why I said it can use to encode some information in this case. This is it. I hope you learned something, and see you next time. Bye.